Okay, good afternoon, everybody. I'd like to begin. The topic of today, although the title of the class is Monte Carlo simulations, what I actually want to talk about today is scattering by more than one particle more than once. So what we did last week when we this scattering was really try to calculate and see how scattering by only one isolated particle behaves. Of course, this issue is much more than that, so we have to scale things up a little bit. So more than one particle and more than once. We are here today, so a big part of that will be discussing Monte Carlo simulations. That is why it is called that in the sketch. All right, just a few warm-up questions for you. So let's go quickly over this. Who can name scattering theories for different particle sizes? Particle sizes then compared to the wavelength. We discussed three. Yeah, go.
So that we scattering?
Yes. And do you also remember when that was valid?
In between the two sizes.
Yeah, that's so you could size. We had this graph where the theories were for small particles, large particles, and in between. Actually, in the size. But actually, me theory is a little bit of a special case because it is valid for all sizes. So it also gives valid results for the very small particles, also for the very large particles, as long as the particles are spherical. Any other theories? Yeah.
Or small particles.
Exactly, for the particles that are really small compared to the wavelengths. And the last one was obviously for that range where the particles were very large compared to the wavelengths. We call it geometrical scattering because we are really particles really big compared to the wavelength. What was so what are in general the inputs for these scattering theories? So let's say you want to calculate some scattering properties. What do you need to know? It's a couple of parameters that not even that many. Okay.
Wave vectors.
Yeah. Okay. So that.
Angle of incidence.
Yeah. Okay. That is true, but that's pretty true. But what properties of the for example, what properties of the sphere, the scattering sphere, do you need?
Electrical field.
No. That would be incident on the particle. What do you need? What do you need to know about the particle? Try to think a little bit simpler. Yeah, the volume or the size, exactly. So that's how big it is, basically. Of course, you need to know the wavelength as well, because and what other property of the particle do you need to know? Do with the diffraction of light. Yeah, exactly, the refractive index. So you also need to know the refractive index of the particle and to be complete also of the medium that the particle is living in. So if it is in water, you need to take that into account as well, or if it is in air, and that's what. So you need the refractive index of both the particle and the medium. And essentially, if you know these four things, for example, if you want to use me theory, these four things are enough. It is enough if you know the refractive index of the particle, the medium, the size, and the wavelength. So you can put it in the computer, and then you will get all these wonderful scattering properties out. So in the formulas, after some time, this function s squared of theta and phi, and that's kind of an important one. So do you know what that function is? What it describes? So I don't need to. What information is in that function?
This is the scattering cross section.
We can derive the scattering cross section from that formula. Yeah, so you could say that the information is contained in that. If you look at the arguments, data and phi, you know what data and phi represents?
They represent the scattering angles, right? One represents the horizontal angle, one represents the vertical angle.
Yeah. So if you have light coming in, it can the angle, the projection of the angle with respect.
With respect to the incoming.
Yeah, so you have an incoming direction, you have an outgoing direction, and the angle in between, the short angle in between is theta, and the rotation angle is phi. Yeah, so that information is also there. So actually, the answer is that function contains everything about the scattering process. It contains how strong the scattering process is, because you can derive the scattering cross section from that. So that was your answer. And it also contains the information about the angular redistribution of the theta and the phi. So how much light gets into angle theta, how much light gets into or it gets into theta in angle theta. Okay, so from that function we could derive the scattering cross section, but we could also derive from that same function the scattering phase function. Can you give a definition of the phase function?
It governs the distribution of the scattering.
Yeah, and only. So it is
It's normalized.
yeah, it's normalized, so it only gives you information about the angles. Note how strong the scattering process is, only about the angular distribution. That phase function was parameterized by a parameter g, the average cosine of the scattering angle. What does it imply if this value g is 1?
Everything.
That's it.
Yeah, that most is scattered in the incident direction.
Yeah, so exactly for g is 1, it's actually all of the light. If it's really close to 1, then it's most of the light. Yeah, so it is the average of the cosine of the scattering angle. So if the cosine is 1, that means the angle is theta, the angle would be 0. So if g is 1, the average cosine is 1, then all the angles are 0. And all the light is just scattered straight ahead. And what does it imply if g is exactly 0? Yeah, in the let's say in the forward directions and the backward directions. Okay, then a philosophical question. So if I say scattering is a complex interaction of reflected, refracted, and diffracted light, what I mean with such a statement.
That the total amount of light that is scattered, some of the light is scattered in three main, it's scattered in three ways. Those being reflection, refraction, and diffraction, and different amounts of light for different situations get different proportions get reflected, refracted, and diffracted. Beyond that, that's all I.
Yeah, well, I'm pretty happy with that already. So the one, so these basically these three effects, these happen during the scattering process. So light can be reflected from the particle. It can also be refracted inside, like in the raindrop, in the rainbow. But it can also be diffracted around the edges of the particle. And all these contributions, so if you then detect that scattered light, all these contributions can interfere. They can some can enhance each other, some can suppress each other. So really depending on the particle size and on the effective index, one of these processes may dominate or not. So they all occur and they all determine the total scattering pattern. That it is so complicated is also why in this V theory calculations that we showed, this phase function was really had all kinds of oscillations and weird minima and maxima in there. That is exactly this interference phenomenon. So that is exactly how this subtle display, so to say, of reflection, and diffraction. So then finally, for the largest of particles, we talked about the extinction paradox. Can we
Means that the scattering cross section is actually twice the cross section, the sort of geometrical cross section of the object that is scattering.
Yeah, so that is the weird result that if you have a very large particle compared to the wavelength, it actually removes by scattering twice the amount of power the light that is actually incident. One part of the light is just let's say reflected. That is the exact amount that is incident on the particle, but due to diffraction and the same factor is diffracted away. So it appears that the particle removes twice the amount of power that is incident on the particle. Extinction paradox. All right. So that was all about single particles. What we're going to do now is to try to look a little bit further than that. So slowly work our way into block tissue. But the model that we're going to use for block tissue is not just let's see if we can model it as a collection of particles. See how the scattering behavior of that collection of particles. So in summary, the properties that we had up until now, so the single particle, absorption properties and scattering properties, and as you will see, they are completely analogous. We had the absorption and scattering efficiency, which was the ratio of absorbed power over incident power, or scattered power over incident power. That's an efficiency that's dimensionless. It's just a number. For absorption, a number between 0 and 1. And scattering efficiency for large particles, the extinction paradox can be true for large particles. From the second property was the cross-section. The absorption cross-section is the ratio of absorbed power over incident density. Scattering cross-section is the ratio of scattered power over incident intensity. And if we know the geometrical cross-section of the particle, we can link efficiencies and cross-sections together just by the geometrical cross-section of the particle. Then for multiple particles, so actually the topic that we want to go there, we already looked a little bit at the absorption coefficient, which was the density of absorption cross-sections, so total absorption cross-sections, divided by the volume. And the same definition holds for the scattering cross-section. So it is the density scattering cross-section. You take all the scattering cross-sections in a certain volume, you add them and divide by the volume. But then, and if we know the density of the particles, so rho, the number of particles to the volume, you can link the coefficient to the cross-section. All right. We saw for absorption that it really matters how the cell is organized, so to say, what absorption coefficient we will measure. If we had a solution of molecules in a cuvette, then the absorption coefficient that we would measure would just be the density times the absorption cross-section of the molecules. But if we had a suspension of particles of a certain size, then it got a little bit more complicated. We could calculate the efficiency of a single particle, which was dependent on the absorption coefficient of the substance that was in the particle. With that, we could calculate the absorption cross-section, and with that, we could calculate the absorption coefficient of the suspension. And here, all of a sudden, we have all kinds of factors that go in there. We have the size of the particle added goes in there. We have the volume fraction of the particles in the suspension. So the organization, how the sample is organized, will determine what kind of absorption coefficient we will measure. So the simple scaling that we have until now stops here. And then, of course, we can ask the same question: if the organization really matters for the absorption coefficient, then probably it will matter too for the scattering coefficient. So the question that I want to address first today is how does the organization of the particles in the sample matter for the scattering coefficient? Any questions so far? This is repeating what we discussed. Okay. So a brief reminder: how did we calculate the scattering coefficient? Well, we started out with the particle that we put in this reference frame over there. It was illuminated with light coming along the wave vector k in the incident direction on the z-axis, and we were going to observe light that is scattered into the direction given by the k scattering wave vector, and for that we try to find an expression. So the scattering cross-section is given by the ratio of scattered power over incident intensity. We assume in this experiment that we know the incident intensity, so what we need to find is the scattered power. The scattered power can be found by putting this big imaginary sphere around the particle and then measuring all the light that escapes through the surface of that sphere. So we have to determine the scattered intensity EF, an integral there, and we sum all of the intensity that escapes through the surface of that sphere. So we have to perform it. So we integrate the scattered intensity of the surface of the sphere. Now, to find the scattered intensity, we first have to find the scattered electric field. And then, if we have the scattered electric field, we can calculate the intensity by this product. So the field multiplied by its complex conjugate. And the expression of the electric field that we found is given here. So the scattered field at some distance r away from the scatterer in the direction given by this wave vector, k scattered, unit vector scattered here. This is proportional to the input field, the incident field. It is inversely proportional to the distance, so that if we square it, it will be inversely proportional to the distance squared, which means it will be a spherical wave as it propagates. The wave number k is in here for normalization. There is some imaginary number e in here for convenience. It does not really matter. There's a phase term that depends on the particle position, on the directions, the difference in direction between incident and scattered light. And there is this function S, this complex amplitude function that describes the directionality of the scatter and the spectrum of the scatter. So this, if we then calculate the intensity from this equation by multiplying it with its complex conjugate, this is the term S squared that we talked about just a few minutes ago. So to obtain the scattering cross-section, then the step as follows. So we try to find the scattered intensity from the scattered field and then integrate that over the surface of that sphere. So squaring that equation for the electric field yields the following: the scattered intensity at the distance r from the particle as a function of the angles theta and phi, because we switched to spherical coordinates now, is proportional to the incident intensity, E0. The function s squared is there in the denominator, and k squared is the wavelength squared, r squared is the distance squared for the spherical. So if we combine these two equations, so plug in the scattered intensity into the integral, you can use the formula for the surface element here. This r squared sine theta and theta and phi in spherical coordinates. And this is the integral that we would have to calculate in order to find the scattered intensity, the scattered power. As you can see, of course, the r squared both drop, which basically means that it doesn't really matter how big we choose the sphere because the size of the sphere goes up. Combining all these all these equations together and rearranging for the scattering cross-section ends up with this expression. So k squared is k is 2 pi over lambda, so that is the wavelength contribution, and all the other information is contained in s squared. Okay. But then in summary, this was so the first equation is again the scattering cross-section. If we normalize the squared function so that the interval will be unity, then we get this new function called the phase function, and the phase function is characterized by the average cosine of the scattering area. And I stop with PG. Okay. So that was the single particle. Now let's suppose that we have more than one particle. We have n particles in a volume V, so that the density, the number density, is given by rho particles per unit. Each of these particles will produce a scattered field, red illuminated, and they all, if the particles are all identical, then the scattered fields will be identical, apart from the fact that the particles are at different positions. So r is the distance from particle E to the detector, so that can change. The total scattered field is then simply the sum of the individual scattered fields, so E1, E2, E3, etc. And the total scattered intensity would then be found by taking this total scattered field sum and multiplying it with this complex conjugate. So even for this bunch of particles, we can find an expression for the scattered intensity, for the collective scattered intensity of these particles. If we have that, we can do the same trick. We can put a very large sphere around that, and we can integrate this total scattered intensity over the surface of that sphere in order to get the scattered power. And from that scattered power, if we know the incident density, we can calculate the total scattering cross-section of these of this bunch of particles. And if we then divide it by the volume that the particles are in, then we have calculated the density of scattering cross-section. That was the scattering coefficient. So the method for obtaining the scattering coefficient is the same as for a single particle, only complicated by the fact that we now have all these individual scattered fields that we have to take into account. Okay, so this is the expression for the field, the sum of the individual fields. This is the expression for the scattered intensity. The total field multiplied with its complex conjugate. You see these brackets over there, so they can, because the electric field itself oscillates really fast, normally our detectors cannot keep up with that. So what you will measure with the detector is some kind of time average over a few of these oscillations. So the brackets can indicate that. And the brackets can sometimes also indicate that you do an average measurement over a larger volume. So other than that, the ones that can just indicate that there is some averaging going on. Okay. So now let's suppose we have two particles. So NS2, and they both give a scattered field, which we can write in the following form. So complex field with an with the magnitude E1 and E2, and with the phase term that depends on the position of the particles. So in general notation, it would be. So my question for you now is: can you now derive for me an expression for the scattered intensity? So E1 plus E2 multiplied with its complex conjugate. What does that yield? Any thoughts already? What's the first step?
I'm coming to u1 squared between the absolute thing plus e2 squared plus 2 u1 e2 cosine base 1 minus 52.
Yeah, so the first step would be to simply fill in, of course, fill in the expressions for e1 and e2, and then for the complex conjugate part, so the second term, you have to flip the sign, flip the sign of the E of the complex number E there. So then it just becomes, then you just have to cross multiply the terms. So E1, the phase term multiplied with E1 with the opposite phase term, and both phase terms cancel. We end up with E1 squared. The same thing goes for E2, and when multiplied by itself. So it's 2 squared. And then the cross terms, E1 times E2, both have, and E2 times 1, both get phase terms with no change. So P1 and P2 are not the same, so that remains there. Then in the next step, we can regroup a little bit. So E1 squared is the same as the intensity by by particle number 1. E2 squared is the same as the intensity scattered by particle number 2. So these first two terms are just the intensities. So the total intensity, these two terms are just the intensities of the individual particles. But then we have this third term. So E1 times E2, we can write that as the square root of intensity 1 times intensity 2. We can group the phase terms together. So we have these two exponential terms, one with a positive E and one with a negative E. And in between is the phase difference between both particles. And this, you know, is the definition of the complex notation of the cosine function. So then finally, this term can be substituted with the cosine of the phase difference between the two particles. So that phase difference, we could also calculate. It's here in the formula over there. So we have two particles that are located at some distance r1, 2 from each other. So some separation. They are illuminated with light coming in across some wave vector as before. And we now observe the scattered field from both particles in some direction given by ks. Then we can calculate by means of geometry that the phase difference between the fields scattered from these two particles is given by 2 times k, in that case then 2 pi over lambda, times separation between these two particles, in sine of half theta, theta the scattering angle. So that phase difference within and as you can see, what this implies is that the scattering intensity will change. So these terms will stay the same. This is just the intensity scattered by individual particles. But the total scattered intensity will change if we, for example, change the separation between the particles, because that goes into that will change R1, R12, that will change delta V, so that will change this cosine term. So what we would measure in intensity would depend on the separation between the particles. Also, if we kept the separation the same, we started looking at a slightly different direction, then also what we would observe could change. So this for N2 that would be the case. Now, if we make this even more complicated, so adding more particles, then we can do the same kind of exercise. So again, we have to take the total scattered field as the summation of the individual fields by the particles. Calculate the scattered intensity by taking the total field and multiplying it with its complex conjugate, like this. So instead of 2 terms, we now have a lot more terms, and then essentially do the same kind of exercise again. So we calculate the total scattered field, integrate it, obtain scattered power. From that, we derive the scattering coefficient, and from that, we derive the cross section. From that, we derive the scattering coefficient. So this scattered intensity for the n particles, if we do that same calculation, if we multiply E first the scatter field by the first particle, if it's going to itself, we get the scatter density of the first particle. The second particle as well, just as we have before, etc., etc., for all the particles. So, the first series of terms will be just the scattered densities by the individual particles. Then, just like in the example of the two particles, we get a series of terms where the field of one particle is multiplied with the exponential of the field of another particle. This summation or this product runs over all the different particles. So we get a term for each particle compared to the other. So we have here a summation, double summation over all the particles, index k, the particle from particle 1 to n. And the second summation goes also from 1 to n, but we exclude in this summation the terms where they are equal, because if they are equal, they contribute to the first set of terms. If they're not equal, they will contribute to the second set of terms. So now focusing on the what's on that subterms again, so that is we can write that as amplitude, in terms of amplitudes and phases. So we have the amplitude of the scattered amplitude of the k particle multiplied with the amplitude of the alpha particle, and there's this phase difference between the two between the k and the alpha particle in there as well. Now let's make it a little bit simpler. Suppose that all particles are equal. That would mean that the intensities of the scattered particles are the same. It also means that the magnitudes of the electric fields of the scattered particles are the same. It is just the phase differences between the sets of particles that will be different. So that simplifies the equation a little bit. So now the total scattered intensity is n times the scattered intensity of one particle, plus again because these two are now the same, we have E particle squared, which is again the intensity of one particle. So we can take that out of the summations. So our result now is the total scattered intensity is n times the intensity of one particle plus n times the intensity of one particle multiplied with this summation of all the phase differences between all the individual particles. Again, regrouping that, we have that the scattered density is n times the intensity of one particle times then 1 plus this double sum. And again, this double sum features the phase differences between the individual particles, and this phase difference between the individual particles depends on their separation at RK elements. This thing between the brackets in green here has a name. It's called a structure test. The symbol is also S. We have a lot of symbols S in this field. Apparently, it is the function of theta, of course, due to the fact that that these phase differences are in there, and the phase differences are determined by that, are also dependent on the name of theta. So it's a function of theta, and it depends on the volume fraction of the particles. So it depends on the amount of particles that are in. That's right. So with that information, now we have this relatively compact expression for the scattered intensity. Now we can do the same steps as before, and finally try to integrate that over this here and get to the scattering coefficient. So there we go. We have to plug in the scattered intensity into this integral and integrate the sphere of the surface. The expression is almost the same as before, except for the fact that we are now considering n particles, and we have this structure factor addition. So you can basically just copy the results that we had before, putting that into the integral, switching to spherical coordinates gives us the expression over there. So again, with n as a theta in green, the only terms that are new now. And it means that we can combine that and get the total scattering cross section through this expression here. So again, n theta within the integral. You can manipulate this a little bit further by multiplying and dividing by this integral term in green. Of course, if you would calculate that integral, that would just be a constant, so it is more complicated than this. But this has a benefit of using both the expression for the scattering cross section of a single particle, which has this integral term. And there we can use the fact that we are now normalizing this theta into the phase function. So we can write an even more compact version of the total scattering cross section as n times the scattering cross section of a single particle plus this term that is the integral of the phase function times the structure factor integrated over the from that, if you then calculate, so that would be the total scattering cross section. The total scattering cross section divided by the volume that the particles are in, the density of scattering cross section, is the final expression for the scattering coefficient. So again, what we found out is that just like with the absorption coefficient, where the organization of the sample mattered, here too we see that how the sample is organized will matter, because a different organization of the sample will give you a different structure factor, and because of that, because the structure factor is different, the scattering coefficient will be different. Okay. So a special situation, which immediately makes all this work seem redundant, is that if there is no average phase relation between the particles, so if that is the case, then this whole double sum, the average of the whole double sum, will evaluate to 0. In that case, the structure factor will evaluate to 1. And if we then look at the expression for the scattering coefficient, if the structure factor is 1, then the second part of the equation is only the integral of the phase function. That integral of the phase function, by definition, was normalized, so that whole integral would evaluate to 1. So what we would end up with simply is that the total scattering cross section of that volume would be n times the scattering cross section of a single particle, and the scattering coefficient would simply be dividing the total scattering cross section by the volume. That would simply be the density times the scattering cross section of a single particle. So if there is no average phase relation between on average there is no phase relation between particles, these phases don't average out, then the situation simplifies. But that is a special case. You cannot generally assume that. When could it happen? Well, if particles in the volume are totally, first of all, if it's a lot of particles, and if they are totally randomly placed. Because if they are totally randomly placed, you can expect that if you have one set of particles, particle 1 and particle 2, that give a certain phase difference, then you can probably find another set of particles, particles 3 and 4, for example, that give the exact opposite phase difference. So on average, that would be 0. So if they are totally randomly placed, then that situation can be justified. But if it's not the case, if the particles' positions are not truly random, then these phase terms and structure factor needs to be taken into account, and then we will have to calculate scattering cross section for this formula. This is a good moment for a break. Because I'll try to illustrate where these random placements or non-random placements come from in the next slide. But let's take a 10-minute break, and then I'll continue. All right. Shall we continue? All right. I know that our room here is not as pretty as the one that you can here. And if you know that if you go to a theater like that, then all the rows and the seats are numbered. So now let's suppose that here in the classroom you went out into the hallway. I asked you to just from the top of your head pick a row number, pick a seat number for you to sit. And you would all come back and we try to go and sit on that number. What would happen? Yeah, what do you think would happen?
Basically, if we assume that everyone is choosing randomly, then some seats would be left empty because no one picked those. Some seats would be just have a single occupant. Some seats would have fewer seats would have double occupants. Even fewer would have triple occupants.
Yeah.
And very occasionally you maybe find one that has 4. But
yeah.
As you get a higher number of occupants, the chances of that ever lower and lower.
Yeah, and it's true. So the situation would look somewhat like this. So we would have, let's say there are X number of guests, and there are number N seats available. Number of seats per row and chairs per row would then be small n. The global density, the number of people divided by the number of available seats would be rho, and the average number of people per row, because you have n seats in a row, would be n times the density. You can calculate, you can derive that the number of people per row will follow a Poisson distribution. Poisson distribution is given by the expression over there, which has both the density in there, the number of occupied seats, that's average. If you then analyze this distribution, then the average number of people in a row would be n small n times the density, and the variance of the number of people in a row would be the same. That is a property of the Poisson distribution. So if I would make a plot of that, the horizontal axis is have the number of people divided by the number of available chairs. So that means that if we go along the horizontal axis, we keep adding more and more people to the room. And on the vertical axis, you see in blue the mean number of people per row, and you write the variance of the number of people per row. But since they can sit basically anywhere, in this case, these two just scale linearly. Of course, there is some issue here with the social acceptability of this situation. So this is not what will happen. What will happen instead is this: one person per row, and some seats are unoccupied, of course. So we can do the same kind of analysis here. So the number of guests is still X, the number of chairs available is still capital N, and the number of chairs per row is small n. The probability of having k, the number of k chairs occupied, and thus n minus k chairs unoccupied, is given by the expression. The number of ways to do that, to occupy k out of n chairs, is given by this binomial expression, the binomial coefficient. So in total, the total probability of having k chairs filled in a row is given by the binomial distribution written here. Then analyzing this distribution, we still find that the average number of occupied seats in a row is given by n times the Lambda density. The variance is now no longer the same as that. The variance now is n times the density times 1 minus the density. So we can make a plot of that as well. Shown here. So again, on the horizontal axis is the number of people divided by the number of available chairs. So along the horizontal axis, more and more people get into the room. As we can see, the mean number of people per row simply increases when more people get in. But the variance, so the variation of the number of people per row, well, at first, if there's only a small amount of people, that will simply grow. But at a certain point, because the seating is basically restricted, you cannot sit on a chair where someone else is already sitting. The variation between the rows starts to grow. And in the end, if all the chairs are occupied, then each row has the same amount of occupied chairs. So the variance of the number of seats is essentially zero. So this restriction here that you cannot sit. You cannot sit in a chair where someone is already sitting, or you cannot occupy volume that is already occupied by someone else. That is a kind of restriction on the system. Now the same thing goes for these particles in the medium. So we said that if we can place particles totally random, then these phase differences might cancel. We would not have to take into account the structure method. But now with particles, basically the same thing as with people, they cannot occupy the same space. If the particles have a certain size, then there is a restriction because they can, at best, they can touch each other, but they cannot overlap. So these phase differences, because of that restriction, there will be restrictions to the positions that particles can take. Because phase differences dependent on the positions of the particles, we can expect that the structure factor needs to be taken into account. So an extreme case of this, where the particles are not placed random, this is in a crystal. So here the scatterers are exactly at the corners of the crystal lattice. And actually, this is you can turn this around in your favor. You can look at scattering patterns by these crystals, and from these scattering patterns, you can infer what the organization in the crystal of these scattering centers was. So this is an extreme example. So there's a very regular placement of the scattering particles in the models that we use to describe tissue. These particles are still placed randomly, but with the restriction that they cannot occupy the same space. So if we look at the medium that contains what are called hard spherical particles, so these are spheres that are really rigid, so they cannot deform, which really means that they can at best touch each other but not overlap. Then we call that a discrete random medium. Discrete because we have discrete particles in there. Random because they are placed as randomly as it gets. So you could visualize that medium like that. So you have a bunch of particles. We take one particle as the reference particle at the center. We can calculate distances to other particles with respect to that reference particle. Now again, in a light scattering experiment, we would illuminate this bunch of particles with light, and each of them would scatter an electric field, which at some detector far away would be observable, and it would have different, it would measure different contributions to different particles because the positions are different. Now, if this discrete random medium is homogeneous and isotropic, homogeneous meaning that the average density is everywhere the same in this medium. Isotropic meaning that it does not matter from which side you look at which side you look at this medium. So really, from this kind of medium, if you would just take out a piece and analyze that, it would give you exactly the same result as if you would take out. If it is homogeneous, nice topic, then the phase differences between the particles will not the phases of the electric fields will not depend on the exact position of the particles, but only on the differences in positions. So instead of looking at the N and the J's, the exact values of that are not of importance. The only thing that matters is the difference. Such a medium is described by what's called the pair correlation function. Also very confusingly, it has the symbol G, G of R, where R is the distance between the individual particles. Pair correlation is a histogram of distances between the particles. So I will take this. This medium here. I will pick a reference particle, for example, the particle in the center highlighted there, and I would simply count the number of particles that I would find within a shell of radius r and thickness dr away from that center particle. Count the number of particles. I would repeat that for different r's, and then I would make a histogram of these particles of these number of particles. It says here normalized histogram between quotation marks because this histogram is it's not really normalized in the conventional sense, but it's scaled because we divide that particle count that we have by the number of particles that we would count if the placing was unrestricted. So it is as if you would count the number of people in the row theater, in the case where only one person sits at one chair, and divide it by the number of people you would find if they indeed were allowed to sit on each other. So that is the normalization. That is just how it is calculated. And a graphical representation of that is shown. So here on the horizontal axis, you have the distances between particles, normalized on the diameter of the particles, so the particles are the same, so it's convenient normalization. And then the histogram, the value of the histogram, G of R, is shown here, curves for different volume fractions, so for different numbers of particles basically in the film. So now if you look first to the black curve for low volume fraction, so only a 10% of the volume is taken up by particles here. Then the curve is a little bit different. It's 0 here from to 1 horizontal axis, and after that it's unity all the way out. How do you interpret that graph? What does it mean? What does it mean that we find a 0 value here?
If the radius that you're measuring is smaller than the radius of the particle, you can really find any particle there.
No, because if that were true, they would overlap. That is not allowed. So for separations up until the diameter of the particle, we're not allowed to find any particles at all. And then after that, the value of the function jumps to 1, and then it continues to be 1 for increasing distances. That essentially means that the likelihood of finding another particle at some distance that is greater than the diameter is more or less constant. So you have the same likelihood of finding a particle at 2 times the diameter, 4 times the diameter, etc. So because the particle volume fraction is relatively low, in principle the particles can take any position. Only the restriction is they cannot overlap. So there is one forbidden region. Now, if we increase, yeah, go ahead.
Is the D in the bottom line,
Yeah.
the R divided by T, what's the T
The
represent?
diameter of the particle.
Okay, thanks.
The diameter of the particle. So if you now increase the volume fraction to, let's say, 20%, so 20% of the whole volume is taken up by particles. Then, of course, first we still have this region. Particles cannot overlap. So up until the diameter, you will not find another particle. But then, at R over D is 1, we see a little increase. So a strong increase, I should say, of the value of the function, and that then slowly decays to B. What do you think that does represent? Means in an experiment when we counted the particles at a certain distance, it means that we apparently count more particles here. And that's because we're now increasing the number of particles. The likelihood that two particles will be very near each other, or maybe even touch, becomes larger. What this shows is that there is an increased likelihood of finding two particles either touching or very close to each other. And then if we're considering distances far away from each other, then that likelihood is more or less constant. Now, even make it worse and go to 50%, so really 50% of the volume is taken up by particles. So you can imagine, so if you would try this yourself with a bucket of marbles, which you would have to fill to 50%, then there automatically becomes some kind of ordering in the sample. So really a lot of positions are going to be forbidden because there is a marble already there. So what you see there is that again, we're going along this axis up until the diameter, nothing is allowed. So there, zero. Then there is a huge likelihood of finding two particles close to each other. And then because if it gets fuller and fuller, and more drukker and drukker in the marble bin, then the likelihood of finding particles at two diameters, so basically particles in a row, is increasing here. There is also an increased likelihood of finding 3 times the radius. And in between that, I'm going to do some dips, because if you start increasing, it gets more and more difficult to fill the volume of the particles. So this, this is what we just discussed. Okay. So what is then relevant to this? We said that it's a bit unfortunately formulated here. We said that if we had a bunch of particles in a sample that scattered light, we would have to take into account the structure factor that describes the different phase differences between the individual particles in calculating the scattering coefficient. These phases were determined by the positions of the particles. Now, this pair correlation function that we just discussed is something that describes the differences between particle positions. It was the histogram of differences of distances between particles. That same distance that comes into the structure. So, of course, these two are related, and they are related indeed through a Fourier transform relationship. It's not exactly the Fourier transform, but it's very close to it. So that means that the non-randomness, the non-exact randomness of particle placement in the sample, ordering incident, if you like, that leads to non-cancelable phase differences. These non-cancelable phase differences are determined by the separations between the particles, and the separation between the particles, the distribution of particle separations is described by the pair correlation function. And then if you take the Fourier transform of the pair correlation function, then you can calculate the structure factor, plug it into the equations we had before, and calculate the scattering coefficient of the scattering coefficient of the sample. Now, when we looked at a few slides back, for argument's sake, this one's fine. So you saw here that the pair correlation function is highly dependent on volume fraction. If you add more particles, you get hugely different pair correlation function. That of course means that if you would take the Fourier transform of each of these individual functions, you would get a different structure factor that is also highly volume fraction dependent. Plugging that into the equation for the scattering coefficient means that the scattering coefficient will also have some kind of dependency on the volume fraction itself. So, yeah, so structure factor goes. What we have here now is this equation is actually shows that we have a structure factor that is dependent on volume fraction due to this whole volume fraction dependency of the pair correlation function. But here in front we have also the density. Density rho, which we could reorganize as volume fraction divided by particle volume. So there's also a term that depends on volume fraction here. So what we get in general, because volume fraction is here and it is here, we get a nonlinear dependence of the scattering coefficient on volume fraction. Which simply means that if it is nonlinear, it means that if we have a bunch of particles and we would measure scattering coefficient, if you would double the number of particles, that does not necessarily mean that we double the scattering coefficient because of this nonlinear scale. So how does it look? So let's look at the equation one more time. This was the total scattering cross section, which we could kind of separate into a part of the scattering coefficient of single scattering cross section, single particles times n, and this term that contains the structure factor. Now this effect of nonlinear scaling is called dependent scattering. And, dependent, basically because it is dependent on the volume fraction. It's kind of historically how the term came about. Also for the scattering coefficient, we've had these equations before. So the scattering coefficient is the density of total scattering cross section. The total scattering cross section is what you would find if there were no phase relations. Multiplied times factor phase function. And the structure function. Okay, let's take a look. So this would be so I showed you the pair correlation function. If you graph it out, if I take that Fourier transform, this would be the result for the structure. So on the practical Fourier pair in this relation is the horizontal axis. So the pair correlation function is the distance, or the normalized distance, of the diameter. On the horizontal axis of the Fourier conjugate, we get the diameter times q. Q that may look familiar. That is 2 times k times sine theta 2. That was exactly the phase difference that we found between two particles. Q times r is the phase difference between the particles. And here too, you can see so how it exactly goes about. It's not so important. What you see here is that if the volume fraction is really low, so 0.1% black line, then the structure factor is unity, is 1, which means that essentially it does not really do anything in calculations. If we increase the volume fraction, then the structure factor gets more wild, gets more oscillations and higher peaks. So that has a higher influence on the scattering coefficient that we will measure. I've made a small simulation that I want to show. You'll see a couple of curves in red and in blue. In blue is our data calculated with mean theory. Mean theory, you know, that is valid for particles of arbitrary size. And what I did here is I calculated it just for a single particle, and then just multiplied it with the number of particles. So not taking into account any of these phases. And then in red you see again mean theory, but then with a structure factor in there. So then just taking into account these phases. Two sets of curves. we'll calculate the scattering coefficient, and we'll also calculate the parent phase function. So the mean theory will give you the phase function of just one particle, and the apparent phase function that takes into account the structure vector is basically the effective phase function of the ensemble. So the ensemble of particles. The check on this is that if we do this whole calculation for very low volume fraction, then the structure factor should go to unity, and both the scattering coefficient and phase function should go to the values that are valid for single particles. Here we go. This is a simulation of a particle of 500 nanometer radius, a silicon sphere. And you see here on the graph, you see a polar plot with the phase function. The light is incident along the 180 degrees, so along here. And this is the distribution of the scattered light in the polar plot. Both in blue, that's a mean theory, not taking into account in red, taking into account structure factor. The volume fraction is pretty low, 5% only. Is not too low, but 5%. In the phase function, you only see very subtle differences here. You can see that there is a little bit of a discrepancy, but in the scattering coefficient, you can already see that the scattering coefficient for just the linear scaling is higher than the scattering coefficient when you take into account the structure factor. So now let's increase the volume fraction. So just keep adding more and more particles to the medium. This would be for 10%. This would be for 15%. This would be for 20%. So what you see happening is that if I don't take anything into account, then the scattering coefficient just scales linearly. If I double the amount of particles, then the scattering coefficient is going. Also in blue, for the phase function, you see no change at all because, it just behaves as the phase function, just scatters as one particle. So you don't see any. On the other hand, if you look at the scattering coefficient, we see here that it does increase a little bit, but the increase drops off. So there's truly non-linear dependency on volume fraction. And also for the direction of scattering, the phase function, the apparent phase function, you see that it gets a little bit flatter. It gets more light, let's say less light gets scattered into the pure forward direction, and it is redistributed a bit more to the side. So let's continue for a bit. 25% and 30%. So by this time, you can see that the scattering coefficient itself is really much lower than if you would just keep a linear increase. And also the directionality of scattering is really changed compared to the normal bits. There is an interesting biological example of this. That is the cornea. So it's a horn fleece of your eye. Basically, it's kind of whitish, as you know. If you look at so what people have done is they've taken histology of that tissue and they measured the size of the cells, that is the refractive index, etc. And then they did the calculation, let's say the calculation, to calculate the scattering coefficient of the light. If they would take that, it would actually, so the numbers they got would actually imply that no light would penetrate at all. So you would not be able to see it. What actually happened is they accidentally did the linear scaling, and they did not take into account that if you have a lot of cells together, they actually scatter like this and not like that. So the true scattering coefficient was much larger this time. Okay, this is it's not just a theoretical exercise. This is an experimental result from the lab of one of our Italian colleagues, where they took milk in different dilutions, so little fats particles in milk to scatter light. So if they increased the amount of fat particles, they found non-linear. Which is the second condition. So it was also obviously experimentally achieved. So what is the takeaway from this part? The takeaway is that we have this effect of dependent scattering or cooperative scattering. It relates to the scaling of the optical properties from the coefficients, etc., with the density or with volume fraction. And in general, this scaling will not be linear. How it will actually perform depends on the structure factor, how that looks like. How that looks like depends on the pair correlation function. So for each and every sample, you would have to first calculate or determine the pair correlation function that the Fourier transform to get the structure factor to plug into your scattering theory. So it's obviously a lot of work, but this is the general thing. The pair correlation describes is a histogram distribution of distances between particles, and these distances directly influence the phase differences between scattered fields particles. So you take the Fourier transform of the pair correlation function, you get the structure factor. The structure factor is the actual function that needs to be included in the scattering calculations. And include that expression, the structure factor, in the integral, where also the phase function is. All right. Any questions about this point before we switch gears a little bit? Okay, well, let me know if you have any further questions. Okay, well, now this all was about scattering by more than one particle. Which I know to complicate things a little bit further. Even I want to look at the situation where light is scattered by one particle and then by the next and then by the next. So even more than once. So the approach remains kind of the same. Build tissue, or we're going to know that this collection of particles and see how far we can get. What we have now is that we can now calculate the scattering coefficient that is associated with this volume V or subvolume V with any of these pictures. That is as far as we go. So if you look at what's going on, so this tissue volume or tissue volumes are characterized by a scattering coefficient, and we will assume that light will be repeatedly scattered on its way from the source to the detector. Now we could try the same approach. We could try to calculate the intensity at the detector, and from that calculate properties that we're interested in. And in order to do that, calculate the intensity of the detector, we have to first calculate the electric field at the location of the detector, and multiply its complex conjugate, and then go through all these motions again. But the electric field at the detector, in this case, will be the summation, will have contributions from all the scattered fields from volume elements within this larger volume. But because we were now considering that light could be scattered more than once, then each volume element, so the scattered field from each volume element itself, is also again a combination of light that has been coming in from all different other kinds of subvolumes. So it gets hugely complicated. Each volume dV is illuminated by all the volumes as well. So if you would want to carry out a simulation like this, that becomes impossible because you cannot. So although this would be the rigorous approach, it's not feasible. So we have to think of something else. So commonly there is two approaches to that. So one is Monte Carlo modeling, which is what we're going to talk about for the rest of today. And the other one is the radiative transport theory, about which I have some remarks on Friday. Monte Carlo, the name, as it suggests a kind of glamorous work, casinos and all, and that is exactly where the name comes from. It derives from the casino, because it's all about probabilities, about randomness, about chance, about luck, about glamorous life, of course. So in a casino, you might want to determine the probability of a win or a loss. So the materials for this topic are largely in writing. So what I will do is try to explain you some of the basics in order for you to be able to read this chapter. To support that is also an extra document, primary notes, which is also on campus. So all the formulas and all the derivations are in there, so you don't need to necessarily write them down. Okay. Let me give you an example. The font needle. Has anyone of you heard from the font needle? Okay, sorry.
Yeah.
Go ahead.
In my MMA bachelor, we have in statistics we need to program this. Like the whole function is supposed to be that experiment. So I have to do that.
Oh, you already did that?
Yeah.
Oh, super. Hello. I'm not going to ask you to do it again, but then you know what the question is, at least. Okay, so I'll go briefly through it. So did
I thought it was part of the MMA bachelor. Not anymore. Oh, I understand.
Well, that saves me a little bit.
No.
The idea is perform. So a needle. So the question that he asked was the room. So it's actually about games people played in bars. There's a room, a wooden floor, which is divided by parallel lines, and then you throw a stick upwards, and you have a betting game between two players. The bet is, will it intersect one of the lines, or will it not intersect one of the lines? And that's a betting game. And then, of course, to make a reasonable guess, you would like to know what the probability is that you would have an intersection with one of the slides. You can calculate that. There is actually the form calculated it already in 1777. If the length of the stick is less than the separation between the floorboards, to make it a little bit simpler, so it either intersects with one line or it does not at all. Then the intersection probability is given by this number: 2 times L, 2 times the length of the stick, divided by P times separation between the floorboards. The funny thing, of course, is a little bit unexpected maybe, is that it depends on P. So where did that come from? But rather than doing this trick in the bar, we can also ask the question: okay, can we use this probability to make an estimate of P? So let's if you pick the length of a stick to be exactly half the separation between the floorboards, we can simplify this probability. The intersection probability becomes exactly 1 over P. So we could do then an experiment where we throw sticks on the floor, matches on a drawn bit of paper, count how many of the matches intersect with the line. So that means that we do that. If we do that a great number of times, we can calculate the intersection probability. Simply the ratio of the number of sticks that intersect over the number of sticks thrown. And if we take the reciprocal, we would have an estimated P. Yeah, exactly. So P, the estimated P, would then be the ratio of the total number of sticks that we throw divided by the number that actually intersected. Okay, try this. It's really fun. So just take a box of a matchbox, draw a few lines on a piece of paper, and just throw and see what happens. I tried it, but I'm not that very good at an experimentalist. Apparently, so my results were not good enough so that I am confident to show you here. But it does kind of work. Of course, you have a good feeling that is you get more accurate results if you use more sticks on a larger piece of paper. It's probably true. People have actually also calculated that. So this is a publication from 1901 in Italian. So I cannot verify if it's actually true what they state. But they said that, or he claims that he needed to throw 3,408 sticks in in order to be able to estimate P up until this accuracy, which is kind of amazing. I did a simulation, a computer simulation, because experimentally it did not work, so I did a computer simulation. And I actually needed about 5,000 of those things to get that same accuracy in the computer simulation. Well, it's a little bit higher, but still ballpark number. So not too bad. So if you have time left, buy 3,000 matches and see what you see. Okay. So this whole idea of repeating an experiment larger number of times, we will use that in order to estimate some properties of the tissue. So what is then the idea of the Monte Carlo simulation of it's kind of a game of pinball where you have photons now visualized somewhat as marbles that bounce around the tissue. So they bounce around between scattering particles or scattering sites here in the tissue. They take random paths from incidence to detection. If you repeat that a lot of times, just like the stick, if you repeat that a lot of times, you can count how many photons in the end make it out of the tissue, and from that you can estimate, for example, the reflectance of the tissue. In order to do that, we need to calculate some probabilities along the way. So the probabilities of step sizes, probability of having scattering events, changing direction, etc. Even short, maybe. That means that we're going to ditch the whole electric field approach. We're just going to look at photons as particles that carry a certain amount of energy or a certain amount of power. I want to briefly take you back to the quantum electrodynamics that we discussed earlier, because there is some kind of analogy. So you remember this slide where there was a mirror that was divided into a few segments. There was light emitted from the light source that made its way to the detector at Q, but there was a screen, detector at P, I'm sorry, and there was a screen there at Q that prevented light going straight from source to detector. Now the lines in the top graph represent, let's say, all possible paths that the light could take in getting from the source to the detector. And we could calculate the arrow for each of these paths. They are shown here. So the more time it took for light to get from the source to the detector, the more the arrow would turn. So you would have longer turns for the segments A and B, so to say, and for the segment G and 0. And then the final arrow for the process of having light going from the source to the detector could be found by adding all these arrows at the tail and then constructing a final arrow from the tail of the first arrow to the end. And then we saw that the light, or the arrows in the middle here, corresponding to the light, the shortest path, they contributed most to this final. So even though all possible light paths from S to P were taken into account, only the ones that you would expect actually to go straight to the middle, they contributed most. This would be the same kind of experiment where you would have a light source somewhere here and a detector, water proof detector, I might say, somewhere below the water surface. Of course, what you would expect is that light would take a straight line to the water surface, then break reflect according to Snell's law, and then hit the detector. You would expect that to be the most important part. You can do the same analysis. You can also try all the other possible paths, and shown there. Calculate the arrows, the likeliness for each other paths, construct the final arrow, and again find that the final arrow is aligned with the most important path that takes the classic part to the middle. And also because these center parts are more important than or contribute more to the final area than these other parts. It doesn't really matter if we just ignore these unlikely paths at the centers, at the edges. So basically, what we end up with is, even though we started rigorously taking into account all possible paths, because most of these paths do not really contribute, we end up with only the important ones, and actually that then implies that light travels more or less as a straight line. Not exactly as a straight line, not exactly as an infinitely thin straight line, because the paths that are a little bit next to that chalk spot also contribute to these two areas. But mostly we can regard it as traveling in a straight line, as a very narrow beam traveling in straight lines. So we can think of, so back to the Monte Carlo simulation, it means that we can think of light traveling in very narrow beams between tissue volumes in the center. So back to that earlier drawing, that means that the dotted lines here now are these very narrow light beams between the different volumes. Just for a few more remarks, and then we'll have another break. Also, what we saw there is that the whole quantum mechanical approach was to calculate, the end result was to calculate the probability, which was the square of the probability amplitude. And the probability amplitude was found by adding together all the contributions of all the possible paths. Even the likely ones, but as we saw in just a few slides ago, we can safely ignore in our application, we can ignore the really absurd ones. I'm not going to go to this whole thing again. We did it in the first class already, but you remember that the amplitude for light going from across A and B and C from the light source to the camera consisted of different steps. It consisted of a turn, a shrink when it hit the surface and turn, and then another shrink at C. So these were applied consecutively to the arrow, to the hand of the stopwatch, which essentially means that's like here. So we have to add all these arrows together to find the final arrow for this. Now the same thing goes. The same thing, an analogy goes for such a trajectory through the tissue. So we have a number of processes. We have the propagation from where the light enters to tissue volume number one. Then we have the scattering event at one, and then we have the propagation to volume number two, etc., etc., etc. So here too, the path of the photon is a sequence of events which all have an individual probability. And to find the probability of this specific trajectory, we would have to multiply all these probabilities together. So that if we do that, it would allow us to calculate the probability of this very specific photon path. So that would be an intermediate result, because to find the final result, the final detection probability, would then be to sum all the possible paths. So this is only one example how light could go with the number of events from the place where it is injected to light is detected. Then again, we would have to formally, we would have to sum. We would have to do this calculation for all possible paths, and then sum all these probabilities, even the weird ones, or even the weird ones, to get the detection probability. And that at first sight seems almost impossible, but then luckily we can do the same thing as with the mirror and with the light hitting the water. We can try to find the paths that contribute most to the final arrow. Instead of considering every possible path, we're only going to consider these most important ones. So that is the approach that we're going to take. So let's take a short break now, and then go into the details. 10 minutes sufficient, or do you want a bit longer?
Maybe 15.
15? Okay, let's do 15. Then we'll start again at 20 minutes to. All right. Just to remind you a little bit further of the whole goal of this exercise of this Monte Carlo simulation. Suppose we have an experiment. This would be Lambert-Beer's law, where we calculate the transmission to a cuvette, and let's say that would be 1%. In terms of probabilities of photons traveling through such a cuvette, we would expect that if the transmission is 1%, we would expect 1 out of every 100 photons to actually pass through the cuvette, and 99 out of 100 to be absorbed in the cuvette. So the total probability of transmission here in this case is an estimation of the detected signal. Now, of course, this was a pretty straightforward situation. If we have a little bit more complicated situation, for example, a piece of tissue in which we place 2 fibers, one that launches light and one that detects light, and the question is, what can I expect to measure in fiber D in such an experiment? Now, the idea of the Monte Carlo simulation is then to calculate the total probability of photons traveling from fiber S through to fiber D as an estimation of the signal that I would get. So if I can calculate that probability, then I can estimate my signal. And that requires me to calculate the probability of each possible photon path, and then add these individual probabilities to find the total probability that estimates my signal. That's the whole. So to find the probability of a photon path, this is then again analogous to the rules of the arrows. If we break up the photon path in a chain of sub-events, so that can be like the cartoon over here, the propagation step, and the scattering event, then followed by propagation step, etc., etc. At some point, the photon may be absorbed, and I stop, and I pick a new one, and I continue the process, or it may be detected. In that case, I score it as a detected photon. Proceed with a new one. So I have to calculate, in order to do this, I have to calculate the probabilities of each of these sub-events. That means I have to calculate the probabilities of a propagation step of a given length, for example, the probability of this step. And I have to calculate probabilities of scattering angle. I have to calculate the probability, for example, that light coming from this direction is scattered at this location into this direction. So I broke it up I break the path up in all these individual steps, calculate the probabilities for these individual steps, and you multiply them to obtain the event probability, and then I have to repeat that many times for all possible paths to estimate my. So it's quite a lot of steps that the computer needs to take. All photon paths to find the total signal. So with this in mind, I can take 2 possible approaches. I can go here to the right-hand side. I can try to find analytical expressions. Try to calculate the probability of let's call it a generic photon path, so a photon path with the number of step sizes and the number of scattering events. And I would integrate, because I would have to add all possibilities. I would integrate over all the variables that are in here. To find the probabilities of such a path and to estimate the signal. That is going to be very difficult. So I have to resort to this side, the Monte Carlo simulation, where I will generate many random photon paths. I will calculate each of their probabilities and add them to estimate the signal. And to make this process efficient, I am not going to draw these paths by hand and then calculate probabilities and then keep going. Now, I want to let the process try to find the paths that contribute most to the probability. So the idea is to find the probability distributions step lengths and of scattering angles, etc., and then sample these so that we can select paths through the tissue. So we're not going to draw them, we're going to generate them by definition, because we sample from the probability distributions. These will be the paths that are most likely, and these will be the paths that contribute. So that way, the process will be efficient. So just one more representation of how that would look like. So I would break the path into the different subevents, which have different color here, and I would have to multiply all these probabilities: probability of step length L1, the probability of scattering at the position, and the probability of scattering events happen, the probability of scattering into a different direction. I would have to calculate more. So these quantities, these step lengths and scattering probabilities and scattering from one direction in the other, they are all treated as random variables. So if I have a random path over here, that means that all the steps that compose such a path are basically random quantities. So step length is random, probability of scattering is random, etc. Of course, they follow a certain probability distribution. Some path lengths are more likely than others. Some scattering angles are more likely than others. So I'm going to sample these probability distributions or probability density functions in order to construct these paths. Okay, if I succeed in that, then this will be more or less the flow chart of such a Monte Carlo simulation. I will launch a photon into the tissue, which means I will initialize photon. I set its position to the boundary of the tissue, and I give it a certain initial direction. Then I calculate based on the probability distribution. I calculate the random step size, which the photon then takes. I do take position. Calculate the angles over which it would scatter. I check with another random number if the photon happens to be absorbed at that position. If it is not, I can continue. If it is absorbed, I need to start over. If it's not absorbed, I can update the position based on the step length and based on the angles, and then repeat stepping that photon into the through the tissue until it's dead. That means it could either be absorbed or it could be detected. Or it could be basically these options could be absorbed or detected. And if that's the case, then I store the data, I start a new photon, a new trajectory, and I repeat that. So this is more or less globally. That would then so this would then generate all these paths given here by all these different colors. Each loop in the situation to generate such a path. All right. So let's look into the terminology of these density functions and probability functions. So the probability density function, P of x, of a certain random variable. In our case, the random variable is going to be step size or scattering angle. Is called P. It's the probability density function. If the value x can take values in certain intervals, so it's a minimum x, a maximum x, then px multiplied by the small size of the interval, small circle of the interval, px dx, is the likelihood that the random variable falls in that small range between x and x plus dx. That's the probability density. The probability density function is normalized by definition. So that means that if x is allowed between the minimum value and the maximum value, that means that if I integrate the probability density function from x minus x maximum, then the answer is 1 by definition. So for example, let's take the probability density function of the step sizes that the photons take between the directions, the dotted lines there. The probability density function itself has units per length. Because if I multiply it with a small segment, the x, then I get something that is universe, and I get the true probability. Okay. For step size, the scattering angle also is scattering angles are also treated as a random variable, and the probability density function for scattering angle we already encountered. It is the phase function. Phase function describes us the distribution of light being scattered into certain angles, and because it is normalized by definition, it serves as a probability density function from scattering into one direction as one, into another direction as two. So we're going to need that. There's one small caveat, or one small step that we need to take. The phase function was normalized, s squared function on solid angles, so both on theta and phi together. So if we wrote, so let's call the solid angle omega, and then this function of omega, we could write it as a function of both these angles, p and theta and phi. So the phase function itself is a function, joint probability function of theta and phi. But what we're now going to be interested in is the probability that's the function of theta only, and phi only. So we have a function that describes the joint probability, but we want to know the probability density of the theta and the phi only. So in order to do that, we need to perform two integration steps. If I want to have the probability density function of theta, then I have to integrate over phi. So I take the whole function p of theta and phi, I integrate out phi, or you could also say allow for all possible values of phi to take place, and then I'm left with something that's only a function of theta. And vice versa, if I want to have the probability density function of phi, then I have to integrate it over the other variable of theta, and that would then be, because we're working in spherical coordinates, that would be from 0 to pi sine theta d theta. So that way, the expressions of the phase functions that we had before, we can convert them into the probability density functions theta, scattering angle theta, scattering angle phi by this approach. So that is the probability density function. Another useful function is the cumulative distribution function of the random variable, and that is the cumulative probability, so the added probability that the random variable falls in an interval that begins with the minimum value up to some value x. So the probability density, which is a function of x, it calculates as the probability from x minus to which. So if you would apply that to the path length, for example, step sizes can take values from 0 to infinity in principle. We could have very large step sizes. So if you would calculate the cumulative distribution function of for a certain value of L, step size L, then it would be the probability that the step size is somewhere between 0 and L. That of course means it's related. So for our variable x, it would be we would take the probability density function and integrate it from the minimum value up to the value that we're interested in. Like this. So now the question is, we have these, we will find later these probability density functions for step size, for scattering angle, phase function. Now we want to construct such a random path. We want to draw random values for the step size and then draw random values for the scattering angle in order to construct such a trajectory. The computer will only give us random numbers between 0 and 1. So somehow we have to convert these random numbers between 0 and 1 into random values for the path length and random values for the scattering angle, etc. That is, of course, the tricky part in these simulations. How do we implement? So I'm going to show you one way that is that's pretty simple, but also pretty expensive in terms of computation time. So it's very straightforward, but it's not very much used because it would take simulations too long. Suppose we have. I'll try to explain that as follows. So suppose we have this function, arbitrary function that is defined from an interval from x minus to x max, and there it has the values y minus, let's say, is f at max, and the maximum is the function. So what would I calculate if I would calculate the integral? So there's the integral of fx over fx dx over x minus x plus. What would I calculate?
The area under the function.
Yeah, exactly. That would calculate the area of the area under the curve.
About the same question. So in the plot that you see there, just the x-axis goes from x minus to x max.
Yeah.
Oh, and the y-axis goes from okay.
Yeah, the subscripts are missing here, but this would be there is some maximum I and there is some.
Yeah.
The area of the okay, so now let's rescale this graph. So I would subtract minimum value divided by the range and do the same thing for the x, and the effect of that would be that both my adjusted x-axis and my adjusted y-axis run from 0 to 1 here, from 0 to 1. Yeah.
But haven't you then done the exact opposite of what you wanted to do? Because you wanted to go from 0 to 1 to minimum to maximum.
I'll go back a little bit later. What I can do now is because now I can use the computer. I can now generate two random numbers between 0 and 1, and use them as x and y coordinates in this plot. Of point in this plot. So I can generate these two numbers and I can place that point somewhere in the plot. So let's say here. Some of these points, because the x and the y coordinates are completely random, some of the points will fall under the curve. Some will fall above the curve, of course. And I can repeat that for a large number of points. Then in the end, I can calculate the area, I can estimate the area by counting the fraction of points that fall below the curve. That would give me an estimate of the area under the curve. And then, of course, I would have to do the scaling back to find the actual integral value. That is true. But you get the idea that this allows me to calculate the area. Yeah, so now if we go. If we now take an arbitrary function again, a probability density function of some variable x, I would kind of do the same thing. I would draw a random number, a uniform random number between 0 and 1 to present the point on the x-axis, so that would be here. And if I would now calculate, so with that probability function f, if I would now calculate f of x random, what would that be? Uniform random number. So what the computer will give you, a random number between 0 and 1, and each value is equally likely in that interval. That's what the computer gives you. So if I would calculate now, e of this x random, that would be the likelihood that this x random actually occurs, because that is the probability. So say I would have drawn a random number, and I would calculate the likelihood of that number, and that would be 0.25. Then for each random draws of this value x, I would accept, because I would accept 25 of them, and I would reject 70 of them, because that is what the probability densities. So it would go like this. I would generate a number between 0 and 1. I would plot it in the graph of the distribution that I want to sample. Random. I would draw two. One point to represent the point on the x-axis, 1 point to represent value on the y-axis. I would then place this point in the graph, and I would see if it falls below the curve or if it falls above. If it falls below the curve, then it accepts the random variable, the random value. So then I work with my random x, and else I will reject it and I will try it. So I will only take the values that fall below the curve. And if for example for this value of x, so that is what I tried to explain in the previous slide. Let's say for this x the value is 25%. Then I would expect that, and the y-axis is completely uniform between 0 and 1. Then I would expect 25 of them to fall under the curve and 75 out of 100 points to fall above the curve. So I would, by accepting only the points that fall below the curve, I would accept only 25%, and I would have my exact probability. So I could then repeat that. So I could generate a lot of x values, and each time see if it falls below the curve or under the curve. If it falls under, I accept it, and if not, then I do it again. And then afterwards, from all the accepted x values, I make a histogram. And if I did everything right, the histogram of x values should correspond to its original probability density function. So that can be just as a side step. That can be a little bit elaborate. So let's say that so the function here is kind of covers the whole range. But let's say that we have a function that goes immediately that is very sharply peaked around 0 and then goes immediately down. Then you can imagine that if I place the points randomly, that I have to place a lot of points just to have a few that are acceptable. So it can take a long time in order to get a sufficient number of points. So let's look how that would work if you would want to calculate, for example, scattering somewhere in this project. This is the Rayleigh phase function. You recognize this one? So it's a function of theta. Even though the formal phase function is a function of theta and phi, you can see that there is dependence only on theta. But formally, the phase function is a function of theta and phi. If I integrate this function over 0 to 2 pi d phi, 0 to pi sine theta d theta, then the answer should be 1. But now I want to sample, let's say, theta only. So I want to have the marginal probability density functions p of theta and p of phi isolated. So to find p of theta, I would have to integrate over phi. So that's the integral over there. So from 0 to 2 pi of the phase function d phi, which is easy because the function itself does not depend on phi, so I can put this whole integral term back here. Only once. Any integral of 0 to 2 pi of d phi is simply a factor of 2 pi. So that factor of 2 pi I can match with 16 pi that is in the denominator, and I end up with this final probability density function of angle theta. So theta only, so 3 over 8 times 1 of this function. For for pi, it's a little bit more complex because then I have to integrate the original phase function from 0 to pi over sine theta and theta. So you can imagine that integral wise, that is a little bit more work. So I will show it to you here. I'm not going to repeat all the steps. You can read that for yourself later on. But the end result is if I fill in the phase function here and I integrate integrate over 5, the end result is 1/2. Probability density function of phi is what is a constant. It's 1/2 pi is a constant, which means that every value of phi is equally likely. Okay, so now let's focus on this theta function. So on this theta distribution, P of theta was 3/8 times 1 plus cosine squared theta. So what is the domain, the range of theta? What values can theta take?
0 to 2 pi. No way, no way.
Yeah,
Yeah, that was the,
exactly. 0 to pi.
the other one was 0.
Yeah, so the range is 0 to pi. Yeah, so even though I plotted it here from 0 to from 0 to pi. It's from 0 to pi. Okay. So how would I then generate random values of theta from uniform numbers from 0 to pi? So how to generate uniform values? The question is, how do I generate uniform numbers on this axis? So I have 0s to 1s, and I want them to be uniform between 0 and pi, so that means not about pi. It's a little bit too clever for myself. Not about pi. Okay. Then the question is, the second question is, what is the domain of p theta? So what is the range that the y values can take? Yeah.
That would be, I believe, because the lowest value that the cosine would take is if theta is 0, so that would be -1. Where would it be? Oh, yeah, no. I'm bad with cosine.
Now, so the cosine can take values between -1 and 1, but it's squared. So that means that so the square takes values between 0 and 1. So that means that the maximum is 2. So that it could take values from on this graph, it could take values from 0 to 6 over 8. Yeah, okay. Formally, you're right. And what I will do then is really only simulate this part. But that's in this case a little bit too complicated. So I'm going to allow it to have values from 0. But the maximum that I'll allow is actually the maximum that it's in. Because now I'm going to do the same trick. I'm now going to generate random points between 0 and 1. These will translate into random points between 0 and pi on the x-axis and between 0 and 6/8 on the y-axis. And I'm going to check for each of these points, does it fall below the curve or does it fall above it? If it falls below, I accept the value. If it falls above, I don't. That's what I just said. So I'm generating a pair of x and y values, and I'm going to accept them if they fall on the curve. And then from these accepted values, I can make a histogram and compare it to the phase function. And actually, this is what you see in this graph over here. So the true range phase function is the curve in blue, and the red dots are then the simulated histogram of these theta values. It looks a little noisy because I just didn't take enough points to have a neat histogram. But as you can see, it clearly follows that. Okay. So again, this is pretty straightforward. You just draw you make a graph of the probability density function that you want to have. You draw two random numbers to generate a point that either falls below the curve or above the curve. If it falls below the curve, you accept the x value. If it false above it, you do not accept the X value, and then you continue. So there's not a lot of. So it's pretty straightforward, but the only drawback is you can have a lot of data points that you reject, so it can take a long time. There's another method which is a little bit more efficient, and that is based on the cumulative distribution function. So remember that if we had a random value x that could fall between some minimum value and some maximum value, then the cumulative distribution function, the x is the probability that the random variable falls within the interval from x minus 2x. Related to the probability density function. So to illustrate, let's take a random value that is the sum of the eyes of two dice. So I'm going to throw two dice. I'm going to add the number of eyes, and that is because the throws will be random, that number will be random. So in that experiment, there are 11 possible outcomes. But some of these outcomes can be obtained in multiple ways. We can realize all the 36 ways in which that can happen are equally likely. But there are 11 discrete possible outcomes. But it means that I can draw a discrete probability density function of this happening. So the sum of the eyes can take values between 2 and 12, because the outcome of 7 can be obtained in multiple ways. That is more likely than the other. I made this a true probability density function because I actually normalized it in such a way that if I would add up all these probabilities, it would be 1, which means that whatever I do, any of these possibilities should happen. Now I would like to simulate this experiment with the computer using only a single random number. So I will draw a single random number between 0 and 1, uniformly distributed with the computer, and I want to manipulate that number in such a way that if I generate a lot of these numbers and make a histogram, then it actually follows this distribution of the sum of eyes. So what I would do is I would calculate the random number. I would manipulate that in such a way that I have a function that transforms the uniform random number into some random value of theta, store theta, and I'll repeat this process, and after that I will make a histogram of the thetas that I generate, and then it should match this input histogram. That is the goal. So we know the probabilities of certain outcomes in this experiment. So the probability of 2 as the sum of eyes can only happen in one way. So that is 1/36. The probability of 3, because there are the sum of 3, we have 2 ways of finding that. So the probability is 2/36, etc., etc. So we could set up an algorithm as follows: we draw a random number between 0 and 1, and if that random number falls between 0 and 1/36, then I would assign 2 as my value of theta. If the random number falls between 1/36 and 3/36, bigger chunk, then I would assign theta as 3. If it would fall between 3 and let's say and then 6/36, then I would assign 4. So graphically, that means that I have this histogram of this probability, discrete probability distribution function of all possible outcomes. I would just stack all these bars along one way, and I would draw a uniform random number, and I would see if I scale these bars from 0 to 1, I would scale in which segment it falls, and that is the probability that I see. So that could be a possible way of doing this. There is an equivalent representation of this. I can so in the top graph I stacked all the stacked on the bars in one line. And what I can also do is take the first one here and then not stack the second one physically on top of it, but put it next to it. So I have the first segment here and put the second segment on top. And then here I would have the first and the second segment and put the third segment on top, etc. So what I do in this way is I construct the cumulative distribution function, because this is the probability of having a value, cumulative probability. So where in the first example I just had them on a line and I draw a random number and see which segment that falls, I can do the same thing here. I can draw a random number here along this x-axis. So let's say it's 0.8. I will see in which segment that falls, and then assign theta is 9. So what I'm basically doing here is calculating the cumulative distribution function. I draw a random number between 0 and 1, and I'm inverting that function, the cumulative distribution function, to see what the random signifies. It's a little bit complicated. So a graphical, another way of graphically representing this. This is what I have. This is what the computer does. It draws a random number between 0 and 1 with constant probability. And this is what I want to sample, a certain random variable x that can take values between a and b, and which follows some kind of probability distribution. What I want to do now, I have a random number between 0 and 1, but I want a random number that follows this distribution, that would follow this distribution. So what we do is we calculate the cumulative distribution function of both random variables. So the cumulative distribution function of a uniform random number would be the area of this curve. So the probability that the value falls between 0 and value. So the cumulative distribution function for the uniform random number is just a straight line. For this variable that I'm interested in, I have to actually integrate to get the cumulative distribution function like this. And the trick is to do a projection more or less along these lines. So I select a random number using the computer. I'm going to project that onto the cumulative distribution function of the random numbers. I'm going to equate that to the cumulative distribution function of the variable that I'm interested in, and then I'm going to read here on the horizontal axis to which value of x on I think in view of the time, I'm thinking a little bit of schedule, because I don't think I'm going to make it everything that I wanted to tell you before the end of class. So that means that I think it was more efficient to stop here and then continue on Friday. That will then mean that we have a little bit, that first on Friday we'll talk a little bit more about Monte Carlo and then go to the next subject, but I think you can so what I'm going to do is I'm going to stop here now and then do the rest on Friday. Yeah.
Question.
Yeah.
Once you're done, can I ask something of the entire class?
Of course. Of course. Okay. You can ask anything. There is some in one of the previous slides I've mentioned what the materials are. So that is a book chapter and a document. I think most of it is readable already by what we discussed so far. So I think we'll be fine with that. I also put the first assignment on Canvas. The same thing goes there. Just read it through. Maybe there's a tiny few things that we haven't discussed yet for that assignment, but I think you can just start, and I think you can just work. The most important part for the assignment for me is for you to work with this stuff. So it's not about making a calculation. It's just getting a feeling of how these things work. So work with it. So do it in groups by all means. Keep the groups a little bit manageable, but I don't mind if you discuss between groups at all. So just work with the material. That's the point. The other question.
Can I go?
Yeah, of course.
So speaking of those groups and speaking of the entire class, something that was missing from this class, which I did have in previous years, was really a common app group for everyone to discuss, for everyone to discuss the lecture, talk about things they didn't understanding, ask their fellow students something, but also in this case to maybe find groups. Because I was missing, I made one. Anyone that wants to join, I can, I have the QR code here, or I can send you a link if you give me some way of sending it to you. So that's something I want to tell. I've made an app group for the study.
You have something on the discussion page on that?
I will. In the, I'll post it in the bio. I'll post it in both.
Excellent. Good initiative.